In a previous video, I quickly showed how tangent spaces in terms of derivations do not work in physics because the units don't work. This is an example of how mathematical structures defined by mathematicians can be different from the type of mathematical structures we need in physics. There were a few comments that pushed back with the same objection, so I decided to just make a video about it. So here's the original characterization of the problem. In differential geometry, tangent vectors are defined as derivations. They are mapped from smooth functions to a smooth function where the resulting smooth function is really the directional derivative of the original function. So we can see the vector as the composition of derivations along the bases. So this would be, let's say, the derivation along x, the derivation along y, and the component tells you basically the angle between those different derivations. Now, the problem with this is that if you just make a simple example here with polar coordinates, you realize that this is not gonna work physically, because here you have the radius and here you have the angle. And the radius is going to be in meters, the angle is going to be in radians, and therefore this is going to be an inverse meters, this is going to be an inverse radians, and you can't sum inverse meters with inverse radians. So the units doesn't work. Now, if you have a geometric space, you can kind of say, okay, I'll multiply by this by a distance, so now I have two distances and so on, you can get away with it. But in something like phase space or other types of spaces where you do not have a notion of distance and angles because the variables on the different axes have nothing to do with each other, then you really can't even make that convergence. So this thing is not really well defined. And so since this does not work with the units, but it just works with numbers, this is something that I would call a mathematical precise definition, but it's not physically precise. It's not something that we can actually work with in physics. Now, the main objection, and most people sort of raised the same objection, they basically said, well, what you're secretly doing when you're summing these two elements, you're essentially multiplied by a meter here and by a radian here, and when you sum them, now this part is unit independent, this is unit independent, you're summing two unitless quantities, and everything works fine. And this is, of course, what I originally thought as well, but it just does not work. This is where we, as physicists, we have the instinct to try and fix things, but we're not fixing it correctly because this does not work. And how do we know that it doesn't work? Well, we just apply the mathematical definition. So in mathematics and physics, a vector space is a set of elements whose elements are called vectors and can be added together and multiplied by numbers called scalars. So this is our vector space V, and there are just a bunch of objects inside here, and there is E1 and E2, and then we have an addition that takes two elements of the vector space and gives us another vector. So for any two elements here, we can sum them and get another elements of the space. Or we can take a scalar number and multiply it, and we have to get another element. Moreover, if we're multiplying by 1, then this has to give you the same element. So if we have 1 times v, we need to get v. So the identity of the multiplication gives you the identity maps on the space. And this is very important. And moreover, we know that in mathematics, a set B of elements of the vector space is called the basis if blah, 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 blah. What basically this tells us is that an element of the basis is an element of the vector space. It's not somewhere else, it's an element of the vector space. So now, let's look at this. Like we have 1 meters times the derivative with respect to r. Well, this is not going to be the same as the derivative of r because we have changed the units. So these operations here can't be the scalar multiplication. And if this is not the scalar multiplication, this element and this element are not the same object. So either this is part of the vector space or this is a part of the vector space. So if you say that V, right, the whole linear combination with 1 meter, 1 radians, this is an element of the vector space, then you're saying that this and this, the two things that supposedly are the bases, are not part of the vector space, and therefore they're not an element of the basis, because an element of the basis has to be an element of the vector space. So the mathematical definition like this does not work. Like, it doesn't follow the mathematical rule. The definition does not work. And that's what I meant by saying that the symbol, the partial r, partial theta, are not elements of the basis, because they can't be elements of the same vector space. Now, suppose you say, okay, whatever, but still we want to think as the derivations as these tangent things, there's elements of the tangent spaces, and those derivations are not going to have a unit. We really want these unitless numbers. That's not what we want in physics anyway. So suppose that I have a temperature and I want to make a derivation, I want to get a gradient of the temperature, right? I will want this quantity to be per unit meter. This has to be the correct unit quantity that I want to study physically. If I just multiply this by a meter, right, because so that I make this unit independent, I don't get the quantity that I want. And doing these derivatives by adding and therefore cancelling the unit, it's actually very misleading, because then you can't tell what the physics is doing. So suppose that I have two different temperature fields, right? One where the gradient is 1 Kelvin over meter. So you go up 1 meters, your temperature goes up by 1 Kelvin. And in this case, instead, it goes up by 1 Kelvin, over a kilometer. So the temperature raises much more slowly. And so let's say that here, in this first case, we are using the x in meter, and we do our derivative unitless derivation, and so we're multiplying by 1 meter. And in the second case, we're using kilometers, and we make this unitless derivation, and therefore we get a kilometers in front. Of course, both of these two cases are going to give us a Kelvin, because we're doing a Kelvin, over a meters times a meter, a Kelvin over a kilometers times kilometer. So we have two things that supposedly should be the same, and they're not the same because the gradient is different. So again, derivations in the way that they're defined in differential geometry are not the things that we want in physics. Maybe it's the thing that people want in math to do some calculation, and it's it's good. But if we want to recover and study the physics, these things are going to be misleading. They're not the things that we want. Okay? So what is it that we want? What is it that we want? Well, I don't have a full theory about it. I can tell you what are the things, some of the things that we want. And in fact, I'm looking for people on the math side to help me clarify the things that we want, so that we can have a version of differential geometry, like that is still differential geometry, but has all these details right, so that when we look at the math, we can make a one-to-one map between the physics and the math, and everything is squeaky clean. So how does it work? So how do units work? Well, the first observation is that a quantity with a fixed units does form a vector space. Again, for a vector space, we just need a set of elements that we can sum and multiply. So if we sum two quantities with meters, and they're going to be, of course, along the same direction, because otherwise, again, we're mapping something that doesn't make sense. But if we have 1 meters plus 3 meters, we're going to get 4 meters. Very good. We can sum meters. We can also get meters and multiply them by a scalar constant, something that is just a stretching or shrinking, so it's a pure number. And so now we have 2 times 3, it gives us 6. Very good. So we have an addition and we have scalar multiplication. You see, this fits the definition, and so this is a vector space. It works well. Now, arrays of quantities also form a vector space. So we have 1 meters and 3 meters together, 2 meters and 3 meters together. We sum them by line, so we have 3 meters and 6 meters. So we can add arrays of quantities. We can also multiply them by a single scalar, and the single scalars is just multiplying both elements by the same number. So good. An array of quantities does form a vector space, and this is what also our intuition is built on. Notice that we can also have arrays with different units as long as the position matches the units. So if we have that the meter is always at the first spot and the radians are always at the second spot, then we can just sum them. 1 plus 2 is 3 and pi plus pi is 2 pi. And we can also multiply by a scalar and everything works fine. So we can do this. This fits the math correctly, and Very good. So now what happens during coordinate transformation? Well, when we are doing coordinate transformation, we take an array, a vector expressed in some units, and we convert it to another vector, another array expressed in different units. So we have a map from meters to meters, meters and meters to meters and radians, and we can go hopefully back and forth. Now what we can't do is take an element here and sum it with an element here. And so we can't do 1 meters and 0 meters plus 1 meters and pi half radians. That's not something that we can do because otherwise we are breaking the rules of the unit. So coordinate transformations are mapped between different vector spaces. So an element here is not an element here, but you can go back and forth in these disjoint vector spaces. What's important to realize here is that the linearity is not preserved. So if we have A, which is 1 meters and 0 meters, and B, which is 0 meters and 1 meters in a Cartesian coordinate, we sum them, we get 1 meter is 1 meter, we get the point C. But if we are in polar coordinate, A is 1 meters and 0 radians, B is 1 meter and pi half radians, and if we sum these two things line by line, we get 2 meters and pi half radians. So, and this corresponds to this point D. So what happens is that, again, nothing weird, that the transformation between Cartesian coordinate and polar coordinate is nonlinear. Therefore, the linearity of the vector space, the addition and the scalar multiplication are not conserved. This is why, you know, when you are working Cartesian coordinate, the first, when you start learning, you're told that there is this position vectors and you can sum this position vector. But then when you do, more advanced courses, when you start doing relativity or other things, the position vector sort of disappears. It disappears because it doesn't work in general, because if you just add a polar coordinate, the problem is that there is no single way to define the addition. You're going to have an addition in polar coordinate and addition in Cartesian coordinate. Now, if you have a geometric structure, you can then define an addition that is compatible with the geometric structure. But sometimes, like in phase space, you don't have directions and angles, or if you have a manifold that it's, that it's just numbers coming from your blood test, again, the relationship between the numbers is, it's just completely different units, completely different physical dimensions, so there is no single way to think about a special coordinate system in which the position vector and therefore an addition works. And another thing that is even more interesting is that coordinate transformations are not continuous over the whole space. And this is a major problem. So if we are in polar coordinates, the angle at the origin is not unique, because once the radius is 0, what is the angle? It's going to be ill-defined. Also, along this part of the x-axis, the angle is discontinuous. It goes from 0 to 2 pi. And so you don't really have a map between all the points to all the points in a way that it's continuous. You don't have what is called a homomorphics. And this is why we need manifolds. So people typically are told that we need manifolds to study spheres. No, it's not because of spheres, it's because of coordinate transformation. So you have a set of points and different set of coordinates, and you need to go from one to the other. And sometimes you can't go always from one to the other, but at least when there is an intersection of the two coordinates, then there in that region you need to be continuous and you need to be able to go back and forth. So this is why we have manifolds. And a manifold is a set of points with different coordinates. The manifold itself has no linear structure. Then you have different coordinates that are defined in patches, which are invertible and continuous between the coordinates and the space in the region where these coordinates are defined. And if we are in a flat space and we have a Cartesian coordinate system, of course, the map is going to be one-to-one, but we have something like a polar coordinate system. There are some points that need to be excluded to be able to have this one-to-one correspondent. And then each coordinate charts have the units and will have its own linear structure. So the space itself does not know about the units, does not know about a linear structure, but each coordinate system has units and has a particular linear structure. That's how it works. That's what we would like to have in physics, because that's how things are. That's what we need to describe. Okay, so this is, for example, let's say that we have a manifold for time. These are all the instants in time, and then we have a manifold for space, for each the position in space. So for space, we're going to have Cartesian coordinate and polar coordinates. So we're going to have two map, xc and xp, that converts from a Cartesian to the space and from polar to the space. And the same thing we have in time. For example, we have a chart in seconds and we have a chart in hours, and we have the two map that, given a second, gives us an instant, and given the hours, gives us an instant. And for example, we're going to be able to convert seconds in hour by going through the space, in the same way that we can go from Cartesian to polar by going through the space and make a map between these two things. So now, if we want to describe a trajectory, then we're going to have a map that, given each instant in time, will give us a position in space, and this is going to be the map on the manifold, on the objects that are sort of coordinate free. And then we can still express the Cartesian coordinates as a map from the seconds, from t in seconds, by essentially go through composition. We take t in seconds, we use ts to get the instant, so then from the instant we get the point in space, and then from the point in space we go and get the point, the values in Cartesian coordinate, right? So this is all nice and clean, this all works, and it's very close to what the mathematics is already doing, and this is the physics that we're trying to describe. Now, what's the issue of coordinate transformation? Can we allow any coordinate transformation, or there are some special one that we'd rather have? Now, suppose that you have a map that it's continuous, but it's non-differentiable. So, for example, you have the axis here, and then you take the lower side on the y-axis and you tilt it, so that now you have a kink here. And so when you have a trajectory here that it's continuous and differentiable, when it gets mapped through this map that it's non-differentiable, it's still going to be continuous, but there's going to be a kink here. So if at this point we had a tangent, what happens is that this tangent gets broken into two. So, you know, we had a direction here, we have a direction for the tangent, and this direction of the tangent is not mapped to a single direction. Now it's mapped to two directions because we have the kink. Now, if we have a differentiable map, well, what happens is that the differentiable map could be curvilinear, it could be like do all sort of things, but what we're going to be guaranteed is that this tangent is still going to be a tangent here. And so even though this tangent expresses a different line through the space, on, in the neighborhood of the point, that tangent is still well defined. So a differential map, the way that you should think it, is that it preserves this local linear structure because it's mapping tangents to other tangents. And this is the property that differentiability gives you, and differentiability on a manifold gives you, because you can keep track of the tangent, you can keep track of these local linear directions, and you get this local linear structure. And moreover, from our standpoint in physics, what happens is that if we have an infinitesimal displacement along the direction, so if we imagine to get infinitely close from this point and a sequence of points, such that at some point we are going to be approximating that change as if we're coming from a tangent, we can do the same approximation on the other side, because now infinitesimal displacement along a direction remain infinitesimal displacement along the direction, because they're infinitesimal displacement, so they're in the neighborhood, they're infinitely close, and since we're mapping tangents to tangents, we are mapping those infinitesimal displacement to other infinitesimal displacement. And then we can do calculus, we can talk about something that it's finite in terms of the decomposition of these finite things into infinitesimal things, which is the thing that we want in physics to have and to use differential geometry and differential calculus for. So If we have a differentiable manifold, we have this notion of infinitesimal displacement dx, or variation. You can call it however you want. But the point is that we have the space and we have Cartesian coordinate, and we have a map that from Cartesian coordinate we can go to the space and vice versa. And these are going to become infinitesimal displacement, like infinitesimal variation. And in the space, we are going to have infinitesimal variation on the space. So these are coordinate-free changes because they just represent infinitesimal variation in the space. And these are infinitesimal variation with units because we are varying the units. Here we are varying the point, and here we are varying the values in a particular unit. And what we're going to want to do here is that we're going to this map, right? This map was mapping finite elements to finite elements. We're going to have a map here that is going to map differentials in units to differential in unitless, right? So what we're going to have is, for example, that we want to say that our dx dy, we are going to multiply by something that takes these two differential and maps them here. So we have a vector space on the differentials, and it's going to be mapped to the vector space of infinitesimal variation in space. And this map then maps the infinitesimal variation in the coordinates to the infinitesimal variation in the space are these things that we typically call the basis vectors, but they're not basis vectors at all. Are things that take something in units and they act on them and they give us the variation in terms of unit-free things. So what we typically call the covariant basis, the covariant basis is actually a map from differentials of physical quantities to differential of the space. And again, we would need a different name because it's not a basis. And we would need some other terminology to make this more precise. But this is, in physics, this is what we are describing. And we also need to be able to go on the other side, right? We need to be able to take a differential in the space and understand how we can express that differential in terms of the units. And so we are going to do the opposite thing. We are going to have a map that takes a differential in the space and gives us the corresponding differential in units. These are what typically called the contravariant basis, and these are the things that map from the differential to the differential of the physical quantities from the differential of the space. So these are actually objects that we are interested in physically, and they're maps from things that have units to things that do not have units. They're not vectors. Those are not the vectors. These are the vectors. The infinitesimal variation form the vector space. And these things are maps between elements of these tangent vectors. So this is what we would like to clarify and formulate mathematically in a precise way, such that they map to the physics in a precise way. And again, there is nothing complicated about this. It just needs to be spelled out. So again, let's go back to the example where we had the time and space and we have a trajectory. And what we have here, we are going to have the differential corresponding in the differential. So we're going to have differentials in time, or variations in time, variation in space, variation in the coordinates, both in the seconds and in the Cartesian. And we are going to have this map, right? We have the map between time and space. Also, this is going to become a map between differentials of time and differentials of space. So this map V is going to be something that, given a variation in time, tells you what is the variation in space. And this is the velocity. The velocity is a map between differential in times and differential in space. In fact, when we're doing physics, any geometric tensor that you can think of can be understood as this, as maps, as something that takes a differential on one side, maybe more than one, in different directions that have different physical meaning, and then gives you a differential on the other side. These are the things that we want to describe. If we want to have a good map between physics and math, if we want to do physical mathematics so that we have mathematics that is physics meaningful, this is what we'd like to have. And this is what I like to build, and this is what I'm trying to do by trying to talk to other mathematicians and other students that want to help me sort of make all of this nice precise, because there are a lot of theorems that seems abstract in differential geometry that once you start looking through these lenses, actually they become physically very concrete and you can understand things a lot better. So again, this is the way of thinking that comes out of the research in the assumptions of physics. So we're trying to essentially go through all these mathematical structures and understand exactly what they mean physically, and understand exactly, do we have the exact mathematical structure that we need? We need something a little bit different. And if you're interested in this type of research, I also have another channel where I go through more of the details. I have a website, and you can also donate on the project if you want to keep this type of research going. So thank you for your attention, and see you next time.